February 27th, 1942. The English Channel looked deceptively calm, the kind of night when nothing should have been moving. But 120 miles south of Dover, a single RAF Whitley bomber was. Its bomb bay carried no explosives, only men. Inside, 30 British paratroopers sat shoulder to shoulder, checking their gear in silence. The man across from them, Flight Sergeant Jack Cox, wasn't thinking about gunfire or the beach below. He was thinking about the strange orders that had brought them here. Their mission wasn't to destroy anything. It was to steal something. Somewhere on that dark French coastline, the Germans had built a device that was spotting Allied bombers long before they reached their targets. Pilots described flak guns opening fire through cloud and darkness, as if guided by an invisible hand. Intelligence had no clear explanation, only intercepted Luftwaffe reports mentioning a code name: Würzburg. For months, reconnaissance photographs had shown a pattern: circular dishes appearing on cliffs, surrounded by cable trenches and generator sheds. The dishes weren't antennas in the ordinary sense. They were parabolic, enormous, almost theatrical in scale, 10 feet across, aimed toward the sea. No one in Britain quite believed the claims that followed, that this device could track a single aircraft 20 miles away, even in rain. So, the War Cabinet gave the order for something Britain had never done before: a raid not to blow up, but to capture. Operation Biting, they called it. The Bruneval Raid. When the jump light turned green, Cox and his team stepped into freezing air. Parachutes snapped open against the night, silent against the surf below. They drifted toward the dark cliffs near Le Havre, landing in silence among the scrub. Ahead, under the cliffs, they could see it, a shape glinting faintly under the moon. The Würzburg radar dish. It looked almost alien in that landscape, smooth, metallic, its curved face tilted upward as if listening to the sky. Cables ran from the base into a concrete bunker that glowed faintly from within. A lone German sentry paced in front of the door. The paratroopers moved quickly. A brief scuffle, muffled gunfire, and then silence. Within minutes, Royal Engineers were already unbolting the radar's central components: the feed horn, the receiver box, the control unit with its circular dials. They worked with surgical precision, guided by diagrams memorized from reconnaissance photos. Inside the bunker, they found more than they'd hoped: technical manuals, calibration charts, and an operator's logbook. Every page, every dial, every tube mattered. By 3 a.m., they had everything that could be carried. Cox and his men packed the parts into crates and hauled them to the beach, where landing craft waited offshore. German reinforcements arrived too late. The paratroopers vanished into the surf, leaving the radar dish standing naked under the rising sun. When the crates reached Britain 2 nights later, they were sent under guard to the Telecommunications Research Establishment in Malvern. The note attached read simply: "Recovered material from Bruneval site, believed to be component parts of Würzburg radar. Handle with extreme care." Among the scientists waiting there was Dr. Harold Klein, an American physicist temporarily attached to the British radar effort before returning to the MIT Radiation Laboratory. He had spent 2 years building radar sets to track bombers, and he thought he knew everything about the subject. But when the Würzburg parts were unpacked before him, precision-machined waveguides, ultra-stable oscillators, and a motorized elevation drive, he felt a creeping unease. "This isn't field equipment," he said quietly. "This is laboratory work." The British engineers nodded. The components were far beyond what they expected from a system built under wartime pressure. The magnetron cavity was tuned to a frequency none of their own radars yet used, 560 megahertz, with an accuracy that implied both advanced metallurgy and exact machining tolerances. When they reconstructed the antenna's curvature and signal feed, the implications hit them like cold water. The Würzburg wasn't just detecting planes, it was tracking them. A perfect, narrow beam. It could tell range within 50 yards, bearing within half a degree. That night, Klein walked through the lab after the others had gone home. The captured parabolic dish leaned against the wall, its surface still speckled with French sand. He stared at it for a long time. Somewhere across that same channel, a German operator had been watching British bombers appear on this very screen, clean, sharp, reliable, while the Allies' own sets flickered with static and guesswork. In that moment, Klein understood what few yet realized. The radar war wasn't about detection anymore. It was about precision, and they were already behind. He made a note in his journal before leaving the lab. If this is standard issue, then we've been outclassed for at least 2 years. Outside, the blackout lights glowed dimly across the English countryside. Somewhere, high above them, the next night's bombers were already gathering. And in a quiet lab in Malvern, the disassembled heart of a German radar stared back, a silent, mechanical eye that had already changed the war. The Würzburg radar arrived in pieces, gray metal boxes marked with stenciled German text, tubes cushioned in layers of oiled paper, the parabolic dish sectioned into 4 curved panels. The crates were unloaded into a converted lecture hall at Malvern, where engineers from both sides of the Atlantic gathered in coats and scarves, their breath visible in the cold morning air. What they were about to assemble would reveal how far behind they'd really been. Dr. Harold Klein stood with a small team of British scientists from the Telecommunications Research Establishment. On the blackboard behind them, someone had chalked a rough diagram. Antenna, receiver, transmitter, display unit. Simple, almost childlike. The real components told a different story. The aluminum feed horn had been precision machined to tolerances finer than 1/10 of a millimeter. Its mounting bracket used a dual-axis motor system with feedback servos that could automatically keep the dish aligned to a moving target. That single feature stunned the group. Allied radar systems still required manual control. A human operator had to track by hand. The cables were wrapped in rubber insulation far superior to British equivalents. Even the screws were numbered for assembly. It wasn't brute force engineering, it was elegance. Klein ran his hand over the dish's inner surface, noticing the polish of the aluminum. This was made in a factory that builds instruments, he said quietly, not weapons. The lead British technician nodded. We thought they were amateurs, building by trial and error. But look at this. Phase lock, frequency stability, feedback control. They've got a whole doctrine behind this thing. By evening, the technicians had reconstructed the main frame. The dish stood upright again, its motor base humming softly as it turned. When they powered the set, a green line appeared on the oscilloscope, steady, narrow, unwavering. It tracked the reflection from a calibration tower half a mile away, and the echo returned crisp, like a heartbeat. Their own gun-laying radar, the SCR-268, could barely resolve a blip at that distance. The Würzburg's signal, by comparison, was so stable that engineers joked it looked like a studio broadcast. One of the British officers, a veteran of anti-aircraft defense during the Blitz, muttered, "Now I know how they hit us in the dark." The data recorder ticked. The numbers didn't lie. The beam width was 2 degrees, 4 times narrower than any Allied radar then in service. Its range precision was within 50 meters. The synchronization between transmitter and receiver was so exact that engineers initially assumed it used vacuum tube locking circuits they hadn't invented yet. But the truth was simpler and more humbling. The Germans had used pure mechanical alignment, achieved through flawless machining and obsessive calibration. It wasn't about complexity, it was about craftsmanship. Klein spent the next days dissecting every component. The transmitter's klystron cavity was compact and perfectly tuned. The intermediate frequency amplifier used an innovative automatic gain control to stabilize echoes, a feature missing from Allied sets until much later. "This," he said, pointing at the narrow amplifier chassis, "is what separates them from us. We built our radars to see. They built theirs to measure one morning. While testing frequency drift, Klein adjusted the tuning dial slightly and saw the echo vanish. He turned it back. There it was again. He marked the frequency difference and blinked. Less than 0.1 megacycle. Their oscillator stability was 10 times better than his own lab's equipment. When the reports reached London, the tone was alarmed but professional. The Air Ministry's summary memo read, "Würzburg system exhibits extraordinary precision in range measurement, capable of directing flak with high accuracy. Countermeasures urgently required." Back in Malvern, Klein began running comparison trials. He set up an SCR-268 alongside the Würzburg in a fog-draped field behind the lab. Two identical test planes flew passes at 10,000 feet. The American radar picked up the target with a ghosted echo. Broad, jittery, uncertain. The Würzburg locked on immediately and held the track flawlessly, even through cloud. Watching the two scopes side by side, Klein understood something that intelligence reports had never fully conveyed. The Germans hadn't stumbled onto radar. They had refined it to an art form. The same parabolic principle, the same pulse timing, the same physics, but executed with such precision that it bridged the gap between experiment and weapon. He wrote that night to his counterpart at M13's radiation laboratory. "They are using parabolas of 2-meter diameter, frequency near 560 megacycles, and have reduced range error below 50 yards. Our systems are coarse by comparison. They can engage single aircraft, not just formations." In Washington, those numbers caused quiet alarm. The United States had invested heavily in radar, but mostly for early warning. Big screens, long wavelengths, coarse accuracy. The Würzburg showed what short-range precision looked like. It wasn't just an eye in the sky, it was a gun sight. Klein began to see a pattern. The dish's exact curvature, the tuned amplifier circuits, the servo control. They weren't isolated innovations. They were part of a system designed from the start for integration. The Würzburg wasn't meant to find targets. It was meant to guide weapons to them. As he dismantled the elevation drive for measurement, a small piece of paper fell out, a maintenance tag from Telefunken, the German electronics firm that built the system. Dated 1941, it bore a technician's signature and a neat note. "Recalibrated for accuracy at 12 kilometers." Klein turned it over in his hands for a long time. A man just like him, another engineer, had written that somewhere in Berlin years before. He wondered if that man had ever seen what his invention did when turned toward a city. At the end of the week, the Würzburg was crated again, this time for shipment to America. The radiation laboratory at MIT had requested the complete unit for further study. As it was loaded onto the transport truck, Klein stayed behind, his coat collar up against the wind. He knew they were already late to the next phase of the war of frequencies, pulses, and precision. And he knew that somewhere in Germany, more advanced sets were probably already watching the sky. He lit a cigarette and watched the truck disappear down the road toward the docks. "Let's hope," he murmured, "we learn faster than they did." The captured radar's green echo had gone dark for now, but it had already illuminated something deeper. The uncomfortable truth that the Allies' technological confidence had been built on a gap they didn't know existed, and the race to close it had just begun. The numbers confirmed what intuition already suggested. The Würzburg's range precision was 3 times better than that of the US SCR-268. Its angular accuracy allowed German anti-aircraft batteries to walk their fire onto a single bomber, even in cloud or at night. The Germans weren't just spotting raids, they were directing entire flak belts in real time. For the scientists at the RAD lab, it was both a revelation and a humiliation. The lab's own radar projects, including the SCR-584, were still in development. They promised similar precision, but none had yet been tested under fire. And yet here stood a functioning enemy model, already fielded, already proven. Klein spent his evenings writing comparison reports. Würzburg achieves narrow beam targeting via mechanical precision, not electronic innovation, he noted. Our advantage in magnetron output is offset by their advantage in control stability. They have built a radar that can aim, not merely detect. But the longer they studied it, the more they realized the Würzburg wasn't an isolated invention. It was part of a system. Its frequencies were coordinated with long-range early warning sets like Freya, and its range data was relayed by telephone cable to central flak command posts. The engineers began simulating those networks on their test range. When they fed multiple Würzburg signals into their plotting computers, they saw how quickly a triangulated position could be calculated. The conclusion was chilling. Any bomber formation approaching German airspace was being watched by at least 3 linked radars, their positions updated second by second. This, Klein told his team during one meeting, tapping the chalkboard where he'd drawn 3 converging beams, is why they're hitting us through cloud. They don't guess. They solve for us. The discovery forced a change in mindset. Until then, radar had been viewed by the Allies as a shield, an early warning system to protect cities and fleets. The Germans had used it as a weapon, an offensive tool of control. So, the Americans began to adapt. The Würzburg's pulse repetition frequency, 3,750 cycles per second, became a target for interference. Engineers at M1T began experimenting with radio jammers that could transmit noise at the same frequency band, hoping to blind the system with static. It was the birth of electronic countermeasures, the invisible duel of signal versus signal. But countering such precision required precision in return. At the operational level, intelligence analysts were mapping every known German radar site across the continent. Reconnaissance flights took hundreds of oblique photographs of coastal installations. Every circular concrete pad, every cable trench was marked. The chain home maps in reverse. Britain now building an image of the enemy's own electronic chain. Klein began to feel the weight of what they'd uncovered. The enemy's technological ambition mirrored their own. For every equation he wrote, there was likely a man in Germany doing the same, with the same tired eyes and coffee rings on his desk. The difference, he thought, was philosophical. The Germans had built machines to see precisely. The Allies would now build machines to hide perfectly. In the months that followed, the Würzburg unit was used for hundreds of tests. Engineers flooded it with interference signals, overpowered it with bursts of microwave energy, even wrapped it in metallic foil to study reflection loss. Every weakness became a new idea for defense or deception. One test, using thin aluminum strips dropped from aircraft, would eventually evolve into Window, the chaff that blinded radar screens across Europe in 1943. At night, Klein sometimes stood outside the lab, watching training flights from nearby airfields. The roar of engines overhead made him think of the men those radars were built to find. Every improvement he made was, in a way, an act of protection. He had started this project as an engineer. Now he was part of a race he could not see, fought in frequencies rather than fire. And though he didn't know it yet, the lessons of the Würzburg would soon lead directly to the most decisive electronic victory of the war, the moment when the Allies finally turned German radar precision against itself. Summer 1943. Somewhere over the North Sea, an RAF bomber crew stared at a sight none of them had ever seen before: the black screen in their radar warning receiver. Normally, when they approached the Dutch coast, the needle would flicker to life, tracing the rhythm of German Würzburg tracking beams. But that night, it stayed still. Nothing. Silence on the instruments. The mission commander checked the calibration, the antenna connection, everything. It wasn't a malfunction. The German radar network, the same one that had once tracked every aircraft across Europe, had gone blind. Back at Malvern and across the Atlantic at M1T, the team led by Dr. Harold Klein had been waiting for that exact moment. It was the result of months of engineering and coordination, the culmination of lessons learned from the captured Würzburg. They had studied its heartbeat, understood its rhythm, and finally learned how to disrupt it. It began with a single question written on the board in Klein's lab. If they can see us so clearly, can we make them see something else? The first attempt had been brute force. High-power transmitters flooded the 560 MHz band with noise, but that proved inefficient. German receivers could filter it out. Then, a British engineer named Joan Curran proposed something different. Instead of overpowering the radar, confuse it. Create so many false echoes that the real ones vanish. She cut thin strips of aluminum foil, each exactly half the wavelength of Würzburg's pulse, and dropped them from a plane. The results were spectacular. On a Würzburg screen, each falling strip appeared as a bright, steady echo, hundreds of them moving at different speeds, blanketing the entire display. It looked like an entire bomber formation had materialized out of nowhere. The idea was tested secretly, then shelved for months. Fear of giving the enemy the same idea delayed its use. But by mid-1943, the RAF could wait no longer. Operation Gomorrah, the bombing of Hamburg, would become the first real test. On July 24, 1943, 791 British bombers crossed the North Sea toward Germany. Halfway across, the lead aircraft released bundles of the metallic strips, Window, as it was codenamed. They drifted downward like silver snow. As they fell, Würzburg operators across the coast called in reports of massive air formations that didn't exist. Flak batteries opened fire into empty sky. Searchlights swung wildly across the clouds. In the confusion, real bombers slipped through untracked. The next morning, intelligence intercepts confirmed what Klein and his colleagues had hoped. The German radar chain had been paralyzed. Operators reported continuous full-screen echoes, indeterminate range. Entire sectors of the Luftwaffe's defense grid had shut down their sets, convinced they were malfunctioning. From his desk in Cambridge, Klein read the after-action summaries and underlined a phrase in pencil: Würzburg operators unable to distinguish targets from interference. He smiled for the first time in months. What had begun as a desperate effort to understand enemy technology had turned into a strategy of deception, and it worked. The British estimated that Window reduced bomber losses that night by more than half. But the victory went deeper than any single mission. Engineers now realized that the radar war had entered a new phase, one where the line between offense and defense had blurred completely. The same frequencies that guided guns could guide countermeasures. The same circuits that measured could be made to mislead. At MIT, Klein and his team began designing tunable jammers capable of mimicking the Würzburg's pulse patterns. The principle was simple but elegant. Transmit a false echo back to the German radar, delayed just enough to make their guns aim short or long. It was precision sabotage by physics. Testing took place in the New Mexico desert, far from coastal interference. The Würzburg unit captured at Bruneval was mounted on a trailer and operated by technicians posing as German crews. American aircraft flew mock raids overhead, broadcasting jamming signals at varying frequencies. Within minutes, the Würzburg's operator reported false targets appearing, ghost echoes that drifted and multiplied. When the team replayed the data in the lab, they realized they'd done something no one had achieved before: electronic camouflage. Klein called it the physics of disappearance. As months passed, these techniques matured into standardized field equipment. B-17 bombers were fitted with carpet jammers. Smaller fighters carried mandrel noise transmitters. Each system was designed with the Würzburg's frequency range in mind. By 1944, entire bomber streams flew wrapped in invisible static, clouds of noise that bent, scattered, and confused enemy radar. Meanwhile, German engineers worked frantically to adapt. They shifted frequencies, narrowed beam widths, and developed filters to detect chaff. But every time they adjusted, Allied scientists followed, recalibrating their countermeasures within weeks. It was no longer a question of who had the better radar. It was a duel of reaction times. The Würzburg, once the most advanced eye in the war, had become its own lesson. It had shown both sides that precision alone wasn't enough. Resilience mattered more. The Germans had built a masterpiece of clarity, but it was brittle. It couldn't lie. The Allies had learned how to make the truth itself unreliable. One night that autumn, Klein stayed late at the test range. They were running a calibration on one of the jamming transmitters. He watched the Würzburg scope flicker with ghost signals, echoes of aircraft that weren't there, illusions created by the transmitter's steady hum. For a long time he stared at the green line sweeping across the screen. He remembered the first time he'd seen that same trace, crisp and sharp in the lab at Malvern, a perfect instrument of detection. Now it was blind, fooled by a trick of its own making. He turned off the display, leaving the room dark except for the faint red glow of the standby light. "You taught us too well," he murmured. By then, the war was shifting again. Allied bombers flew deeper into Germany each week, guided by their own improved radar sets. The same physics that had once terrified them was now their shield. And for Klein, the captured Würzburg had become something more than a machine. It was proof that the future of warfare belonged not to the biggest guns, but to the best minds, to those who could turn understanding into advantage and precision into power. By 1944, the Würzburg radar was no longer just a captured artifact. It was a blueprint that had quietly reshaped Allied science. The engineers who'd spent nights staring at its green echo now used that knowledge to build something better. Radar systems that could see farther, lock faster, and survive interference that would have blinded their predecessors. And though the Würzburg's metal frame sat disassembled in a Massachusetts storeroom, its design had already spread like a fingerprint through every Allied radar lab in Britain and America. At the Telecommunications Research Establishment in Malvern, the British had already turned imitation into innovation. The SCR-584, America's response to the Würzburg, rolled out of its first factory that spring, a compact truck-mounted radar with an automatic tracking system, a magnetron transmitter, and a precision servo drive modeled directly on the German mechanism. Its pulse power was 10 times higher, its accuracy within 25 yards, and its range nearly doubled. The lessons of the Würzburg had been absorbed, digested, and refined until they no longer looked German at all. Dr. Harold Klein, still stationed at MWRT's radiation laboratory, watched the evolution unfold from the inside. He'd spent 2 years surrounded by blackboards filled with equations, test logs stacked waist-high, and a single note taped above his desk. They used precision. We'll use adaptability. It became the unofficial creed of the Allied radar effort. Every system was designed not for perfection, but for flexibility. Frequencies could be shifted on the fly, filters swapped, circuits retuned. No more single-purpose sets. Every unit could evolve as the enemy evolved. Klein's lab began referring to it as elastic engineering. It was the opposite of the Würzburg philosophy, and it worked. The SCR-584 debuted in Europe in late 1944, mounted on half-tracks and deployed behind advancing lines. American GIs nicknamed it the Electric Eye. It could track an incoming aircraft automatically and aim anti-aircraft guns with uncanny accuracy, day or night. In Italy, soldiers watched in amazement as the guns followed a target with no human hand on the controls. What they didn't know was that its servo system, the very heart of its aim, had been inspired by a captured German radar from 2 years earlier. Klein received one of the first field reports that winter. System effective against V-1 flying bombs, it read, predicted impact zones within 0.2 miles. The Würzburg had once guided German fire, now its descendants were guiding Allied shells. But perhaps the most profound change wasn't on the battlefield, it was in how scientists thought about war itself. For the first time, they saw it as an engineering contest fought across frequencies and feedback loops. Radar wasn't just an invention anymore, it was a language. And every pulse sent into the air was part of a conversation between opposing minds. The late-war radar maps of Europe told that story better than any report could. Where the Würzburg once stood alone on concrete pads along the French coast, new dots now filled the continent. British and American mobile sets sweeping the skies, plotting enemy aircraft and artillery. The electromagnetic spectrum had become a battlefield of its own, and the Würzburg had been its opening salvo. At the same time, Klein's work at M1T was shifting toward the next frontier, microwaves. Using cavity magnetrons, his team built experimental 3-centimeter radars capable of resolving ships, aircraft, and even periscopes on the sea surface. These new sets, compact and agile, would form the backbone of post-war air traffic control and early missile guidance. They were, in every way, the grandchildren of the Würzburg. When the war ended in May 1945, Klein attended the final debriefings at the RAD lab before its official shutdown. The engineers who'd once studied the captured German set were now discussing a global radar network, peacetime navigation, and weather observation. The instrument that had guided guns would now guide storms and ships. In the cluttered conference room, Klein listened as younger scientists talked about television frequencies, civilian air corridors, and meteorological radar, concepts that hadn't even existed when the first Würzburg was captured. He smiled quietly. "We built weapons," he said to a colleague afterward, "but we left instruments." The irony didn't escape anyone. The most destructive technology of the war had become one of the most peaceful tools of the post-war world. Still, for Klein, the lessons of the Würzburg never faded. It had shown him the power of precision and its limits. A perfectly tuned machine could be blind to anything outside its design. The future, he believed, belonged to systems that could think, adapt, and learn. In that sense, the Würzburg had been both the end of one era and the beginning of another. Years later, when the Cold War dawned and radar became the nervous system of every nation's defense, Klein's papers were still being cited. The terminology had changed: electronic warfare, signal intelligence, countermeasures, but the core truth remained. Every radar was both an eye and a target. Every signal both a question and a vulnerability. On his last day at MIT, Klein walked through the warehouse where the disassembled Würzburg still sat, its dish propped against the wall, its cables neatly coiled. Dust had settled on the once bright aluminum. He rested his hand on the edge of the dish and traced the faint scratches left by a Telefunken technician 3 years before. "This started it," he said softly. and it taught us how to listen. Outside, the rain fell in steady rhythm, like the pulse of a radar sweep. For the first time in years, the world was quiet. But in that quiet, the next race was already beginning. And out of curiosity, I would love to know, where are you guys watching from? Please subscribe to the channel if you liked the video. I put a lot of effort to bring you factually correct and lesser-known stories of the past. We'll see you tomorrow with the next one.